welcome to the Noesis Interactive Vehicle Scripting tutorial. In this module, you'll learn all about vehicle scripts in the source engine, what the values do, how to change them, how to get the results you want, and what you can do if just scripting isn't enough. A scripting reference guide is also included. It's a compendium of all of the scripting values with information on how to use them effectively. This tutorial is an accompaniment aimed to provide a more hands-on education by stepping you through a few simple mods, as well as giving you some ideas on where to go next. Between this and the reference guide, you should have everything that you'll need to start creating vehicle scripts in the source engine. Before we begin, you should know the limits of what is possible with scripting and be sure that it's really the way you want to go. The source engine is split up into three distinct parts. Logic and algorithms are written directly in the code, constants that those algorithms use are in the script, and graphics information is stored in the MDL files. If you plan on completely overhauling the way a vehicle looks or behaves, you'll want to create a new model file or modify the code. However, if you want to make some tweaks to an existing vehicle's systems, scripting is the best way to do it. Vehicles in the source engine already have a number of existing systems built in, and the values that control them are all stored in script. Everything from the strength of the suspension to the power of the engine, and even some of the physical constants are in the script files. It can be a lot of fun to simply mess around with the various script properties, making floating, inertialess cars, but to see the effect of your script changes, you'll need a test map to drive around in. To help you be able to focus on just scripting, we've included a simple map file for just this purpose. If you open the map file, named testdrive.vmf, in Hammer, you'll see that it contains a buggy, a jumping ramp, some speed bumps, and some combined soldiers for you to plow through. If you double-click on the buggy, you'll bring up the Object Properties windows where you can change a number of things, including the vehicle script file being used. This allows you to make maps where multiple instances of the same vehicle type have different behaviors. For now, leave it set to jeeptest.txt. This is the script file used in the official Valve maps, and it's a good reference point to start from. Note that if you make any changes to the map, you'll have to recompile it for them to take effect. This is not the case with just script files, which only require that you restart Half-Life 2 so that the most current version can be loaded. Now that you've seen the test level, let's start changing the vehicle some. For this tutorial, we'll be trying to get the most performance possible out of the buggy. This means not only higher acceleration and top speed, but better handling as well. Let's start by opening up the script file that the buggy in the test map is using. Assuming you didn't change it, it should still be jeeptest.txt. You can find the file in the Vehicle Scripting mod directory under Scripts/Vehicles. Before you change it, though, you may want to make a backup copy so that you'll have a solid reference point to go back to. Once you've done that, open up the file and take a look around. Let's start out by increasing the raw power of the engine. Horsepower is a measure of an engine's output, so let's try changing the horsepower value from 350 to somewhere around 1000. This should give the buggy a lot more acceleration. That's more like it. With a huge increase in engine output, we're accelerating much faster. There's a problem, though. Notice how if you try to turn when accelerating, you don't have very much control. This sort of unexpected consequence is one of the most difficult things about working with script, and such problems usually require some understanding of physics to resolve. The best way to figure out what's happening is to go through step by step. In this case, our problem is that we can't steer. Since steering is done with the front wheels, a good first guess would be that something was wrong with those wheels. They're still moving, so the other option is that they're not contacting the ground firmly enough. Now that we have this idea of what might be wrong, let's see if we can fix it. One obvious way to get better contact with the road would be to simply increase the weight. By increasing the script value mass override, we can do just that. Let's try it with a value of 1500. Well, that almost worked. We had better handling, but when we ran into the wall, everything went crazy. The physics system in Half-Life 2 is quite complex, but even it has some things that cause it to freak right out. With all that mass and acceleration, it may have been too much for the suspension to handle, or there might have been some sort of rounding error. On the bright side, we now know for sure that the front wheels need better contact, but increasing mass isn't the best way. Using a little bit of physics, we can figure out that the increased power of the engine would have increased the torque on the wheels, and therefore also increased the counter torque on the car. Conveniently, there's a value that can alter the counter torque in the script. Since 1 is making the wheels go up, let's put in -1 and make them go down. Now that's the kind of result we were looking for. We can keep the counter torque where it is for now, as it gives us some pretty nice results, but what about going the other way? If you wanted to, you could increase the counter torque value so that when you accelerated, you actually got off the ground and popped a wheelie. The exact value that will work for your vehicle really depends on the other things that you've changed, but if everything else is at its default setting, a counter torque value of 3.1 should work very well. This is what makes script so much fun to play with. Change a number here and there, and you can wind up with some pretty radically different behavior. Be careful though, because frequently a lot of things go together to create the final behavior, so you only get so far unless you understand a bit of the math behind how the simulation works. If you're already familiar with how real cars work and the basic physics behind their behavior, this section will be mostly review for you. If you're not, this will be one of the most valuable parts of this tutorial, since understanding the basic physical systems in a car is essential to understanding many of the script properties. This section will include some mathematical formulas, but only to help illustrate the basic relationships of the various systems, so you shouldn't worry about memorizing them. You should be aware that some of the examples and formulas presented here are rather simplified and not completely accurate. They do still represent the more general relationships, though, which should be enough to help you write and debug your scripts. To start with, let's examine one of the most basic and noticeable features of a vehicle, its acceleration. To find the acceleration of any object, you must know the force being applied as well as its mass. The acceleration is simply the force divided by the mass. In the case of these vehicles, the force comes from the engine making the rear wheels spin and push the car along. This brings up another kind of force called torque. Torque is the rotational equivalent of force. While force is usually directly measured, torque can be found by multiplying the force applied to an object by the distance from the center of the object it's applied to. This is somewhat confusing on the surface, but it can be very intuitive in certain contexts. For example, if you have two wrenches of different lengths, the longer one is clearly going to require less effort to move the same bolt. Though it's not as commonly thought about as force, torque is everywhere, and it's an important part of the source engine. Moving on, just as torque is the rotational equivalent of force, rotational acceleration corresponds to linear acceleration. Also like force and torque, they behave in a similar but still very different manner. Rotational acceleration can be approximated by torque divided by mass, and that's good enough for our purposes. Another thing that's come up in previous sections is friction. To handle properly, a vehicle needs a good grip on the road, which is to say it needs to have a lot of friction. Friction is determined by two things: the friction constant for the two contacting surfaces, and the normal force, which is the amount of force acting perpendicular to the contact surface. The friction constant's really just a measure of how sticky some combination of objects are, and you can think of the normal force in the equation as modeling how two objects are harder to slide against each other if they're being pressed together harder. Friction's the key to good handling, and without it, the car will just slide along with the wheels spinning in place. Finally, Newton's third law also applies, and can cause some serious trouble if you don't account for it. It states that for every action, there's an equal and opposite reaction. In the last section, this was the root cause of our front wheels losing contact. Since the engine exerts torque to make the rear wheels spin, Newton's third law dictates that they must be exerting an equal force in the opposite direction on the engine. Since the car is so much more massive than the wheels, the rotational acceleration of the car wasn't noticeable until we increased the power of the engine. Aside from physics, the other thing that can be quite helpful in understanding vehicle scripts is understanding the way that cars work. There are three main components which control the delivery of power to the wheels from the engine, which are connected sequentially. First, the engine generates rotational power, which is measured in revolutions per minute. A typical car engine runs anywhere between 3,000 and 6,000 RPM. Then, using one of the gears in the gearbox, the output of the engine is multiplied into faster but less powerful movements, or slower but more powerful movements, before the power is transferred to the back of the car and split between the two wheels. This step also works through a series of gears, and the power ratio of this final stage is called the axle ratio. The purpose of this complex arrangement in a real car is that it lets the car change speeds without significantly changing the engine's output. If there were no variable gears, the engine would simply have to spin faster and faster, and it would eventually overheat and explode. Vehicles in the source engine work in a similar way. However, thanks to the fact that they're only simulations, they don't have to worry about their engines exploding, and so don't have any need for variable gears. The power of the simulated engine is determined only by the horsepower and maximum RPM script variables, and the whole powertrain is reduced to a single constant multiplying factor to make the simulation run faster. This is why only the first gear listed in the script file actually does anything. Another side effect of this simplification is that the source vehicles don't have the same trade-off between power and speed that makes real cars accelerate better at lower speeds and limits their top speed. Instead, the maximum speed of a source vehicle is controlled by a limiter that's set in the script. Aside from these minor changes, the engines in source vehicles behave very much like those in real cars. Now then, let's see if we can't put all this information to good use. We've learned that there are three things that can affect the power being delivered to the wheels: horsepower, revolutions per minute, and a change in the final gear ratio. To get the best acceleration, we know we want a high horsepower and low RPM, so let's try making that happen. Set the horsepower value to 2000 and lower the max RPM value to 1000. We also know that this will put a lot of torque on the tires, and therefore a lot of counter-torque on the car, so let's be sure that the counter-torque value is still at -1. We could also change the gear ratio if we wanted to, but that would only shift the power around instead of increasing the overall power available. Finally, you should set the max speed value to something reasonably high to make use of all this additional power. And counter-torque rears its ugly head again. It looks like we created the Roadrunner in vehicle form. It's certainly fast, but if you want to have it behave in a less comedic manner, try setting the counter-torque value to somewhere between -0.5 and 0. Otherwise, I'd say that our little experiment in vehicle acceleration tweaking seems like it went perfectly. Unfortunately, it didn't. There's one other nasty problem that can come up as a result of high torques. If the engine power ever gets too high, your car will actually do a barrel roll if you put on the handbrake while pressing forward. It only comes up intermittently, but to be sure, put your max RPM value back down to 2000 and reduce the horsepower to 1000. Since it's such a strange error, though, try to keep this in mind if your car ever starts randomly jumping and you can't figure out why. Moving down the script file and away from the gears and engines, we come to the booster. Boosters are the easiest parts of the script file to change, in my opinion, because they are for the most part self-contained. No matter what values you put here, as long as source doesn't crash on reading the script, it won't affect anything outside of the booster. You simply set an acceleration, maximum speed, duration, and a cooldown time, and source takes care of the rest. You can also switch between directly applying a forward force to the vehicle or temporarily increasing the power of the engine with the torque boost value. There are obviously some limitations, such as the inability to change the direction of the boost to, say, up, but you can make some pretty fun little modifications regardless. Say we want to change the way the vehicle drives so that you're either going full tilt or braking. To do this, we would have to disable normal drive, but we can't. So the next best thing to do is make it useless. If we set the horsepower to 0, we can't use torque boost, so we'll set it to 1, since a 1 horsepower engine isn't going to have a whole lot of luck moving an 800 kilogram vehicle. Next, we up the duration of the boost from 1 to 120 so that it lasts a good long time. Finally, we set up the boost itself. Since we want to use torque boost, we'll set that to 1, and since in torque boost mode the force is multiplied by the engine horsepower, we'll have to set it to something very high, say 500. You should also set the max speed value suitably high, probably somewhere in the 80 mile per hour plus range. Make sure you have the counter torque at 0 for this one, and to avoid some of the bizarre problems that crop up with high torque values, you should also put the engine RPM back up to the default 3000. Personally, I had a lot of fun with this mod, driving the car around little test rooms, skidding around and smacking into combine soldiers. I will grant you, though, it is pretty hard to control. This is where the steering section of the script comes in. While many of the steering values, like the multiple gear listings, are old holdovers that are no longer hooked up to anything, the few that are can be quite useful. Going back to our high-performance buggy, if you hadn't noticed, it currently tends to wobble quite severely when it starts going too fast. This can be fixed by increasing the fast dampen value, which also gives the vehicle a much more stable feeling. For this example, I set it to 1.5. Another issue that has come up several times, the skidding and lack of friction, can be fixed to a large degree by setting skid allowed to 0. The value name is something of a misnomer since disabling it won't actually completely eliminate skidding, but it will severely reduce it. While we are discussing the steering values, you can also alter the centering force of the steering wheel with steering rest factor. If you set it to 2, it'll be completely up to the user to change the direction of the steering, and it allows for much more accurate, if somewhat difficult to use, controls. Surprisingly, the axle values play an even larger part in how the vehicle handles than the steering values did. Every vehicle script needs to have 2 sets of axle values, or blocks. The first one defines the front axle, and the second one defines the rear axle. Within each axle block are the values defining the wheels on that axle, the suspension, and the axle's overall power. To make the script more readable, the wheel values and the suspension values are both contained in separate subblocks. The wheel block controls every aspect of the simulated wheels in an axle. It's important to note that these are not actually the same wheels as the ones that you'll see in the game. Vehicles in Source use a separate, invisible physics vehicle with spherical wheels to model the physical behavior separately from the graphics representation. These values control that vehicle, and as such it's important that the radius values in your script match the radii of the wheels in your model. However, to enable things like hovercraft that don't have any visible wheels in the first place, this is not so much of a requirement as it is a suggestion. Moving on, the inertia value is a great way to prevent tipping when making high-speed turns. If you set it to -10 or so for the front axle, you should be hard-pressed to flip your car by swerving alone. On the opposite end, setting it to +10 can make your buggy into a fairly effective bowling ball to pitch at the Combine soldiers. The second axle subblock controls the suspension. The first and most important thing to know about changing this subblock is that you shouldn't if you can avoid it. The suspension values, more than any other script setting, are very volatile and have the potential to render your car completely immobile at best if you're not careful. Even if you are making a vehicle from scratch, it would probably be best for you to copy the existing values from the buggy or the airboat. That said, there are a few things that can only be accomplished through the suspension values, and if you're armed with a little bit of information about how suspensions work, you should do alright. For example, let's say we wanted to make the buggy more of a lowrider. The spring constant value controls how stiff the springs in the suspension are, and so if we make them weaker, the body of the car should sink since the suspension won't be able to hold it up as effectively. You'll have to be careful not to make it too low or the body will scrape the ground, but a value of 25 or so on the rear axle should be just right to make a low rider. As you can see, we did manage to make the buggy more of a lowrider, but it's also making the buggy very tip-prone. We've already covered several values that could fix that, such as the inertia, so moving on to the obvious next question, what happens if we increase the spring constant instead of decrease it? Like I said, the suspension values are very volatile, and at a value of only 150, the car will start to go nuts. Since we're aiming for the best performance, I recommend setting the front spring constant lower than the rear one, and not messing too much with the other values. 60 and 80 respectively gave me some nice results. This ensures that the steering wheels have somewhat better contact with the road without making the entire car sag. The last relevant value is the max body force. You can think of this as the maximum amount of force that the suspension can absorb before it's transferred into the car itself. In most situations, this value won't severely affect the performance of your vehicle, but if you're planning to drive over a lot of bumpy surfaces or off of a cliff, then you'll want to set this fairly high. With both of the sub-blocks out of the way, let's move on to the last two values in the axle section. The torque factor value is not quite what you would expect at first glance. Though it is simply another torque multiplier, the fact that it can be different for each axle opens up a lot of possibilities. While increasing both values together does make some difference, the really important thing is the percentage difference between them. You might expect the best performance to come from very high power on the back wheels, simulating a rear-wheel drive, but it doesn't quite work out that way in the Source engine. If you've noticed, the car tends to drift a bit to one side. This is one of the unfortunate consequences of the Source engine's simplified physics. In order to steer properly, a source vehicle's power needs to come from the front wheels. Finally, the brake factor value is a constant braking force applied to that axle. It would make the car somewhat faster to set it to 0, but the result would never slow down unless you hit the brake, which is very unintuitive for a normal car. I recommend testing out several different values to find the feel that you like, but for our supercharged buggy, we left it at the default 0.5. This concludes the Noesis Interactive Source Vehicle Scripting tutorial. I hope you found the answers you were looking for, and if you have any more questions, please visit the forums on our website